Welcome back to Department of Physics, Sri Shivaji Education Society, Amravati Science College, Nagpur. Today we are going to deal with Reynold transport theorem of fluid mechanics, and here we are going to have approach of system and control volume for the discussion. Let us now deal with Reynolds transport theorem. The Reynolds transport theorem provides a link between the system approach and control volume approach. We should first understand what is system approach and control volume approach. System, which actually means control mass, is a quantity of the matter for study. The boundary of a system can be fixed or movable. System can be considered open or closed. Whereas control volume is the volume of the space for study. The surface of control volume is closed, and this surface we shall call control surface, CS. Surface is defined as fixed or movable. System focuses on a set of fluid particles, whereas control volume focuses on fixed volume surrounded by closed surface, and the closed surface is defined as fixed or movable. So here system that contains fluid particles, matter, mass, we are representing by red balloon, and control volume, which is fixed space, is identified by the territory of this blue line. Let the system is being represented like this by the red balloon, and we shall consider control volume non-deforming. It means that as a function of time, this control volume is not undergoing any deformation. Now let us begin our discussion with the state that system and the non-deforming control volume coincides at some point of time, say t. Now here the extensive property capital B is mass, momentum or energy. All these quantities we consider for writing conservation principle. The law of conservation of mass we often use, the law of conservation of momentum we often use, and the law of conservation of energy also we often use. So extensive property is the property which is depending upon the parameter mass. This extensive property in general we shall represent by the letter capital B. The intensive property we shall represent by small b, and it is the extensive property per unit mass. So small b is equal to big B per unit mass, or the more appropriate point form of the same representation is B equal to dB by dN. That is, intensive property is extensive property per unit mass. So mass per unit mass will be unity. Similarly, momentum per unit mass will be simply velocity, and energy per unit mass we shall call specific energy, being represented by small e. System and non-deforming control volume coincides at a given point of time t, then B system at t is equal to B control volume at t. So both the areas, both the volumes, they are encompassing each other. We represent that B sys equal to BCV. This is an important equation we are going to refer. Let us now consider that as time advances, the system, that is control mass, is forwarding into right direction as compared to the control volume, which is fixed region of space, and we have imposed that it is non-deforming. So at a later point of time, the picture is something like that is appearing on the screen. System has moved ahead of control volume, and the boundary region of CV and Cis is represented by A, F, C, and the another boundary continues as C, D, and A. So here we have two regions. Region 1 is a part of control volume, and region 2 is a part of system, and we have to account for this to write the equation B cis and B CV at the advanced time t plus dt. So here look at the equation at the bottom. B cis at t plus dt is equal to B CV at t plus dt. B CV has not changed at t plus dt, but because of the advancement of system, we have to subtract the region 1 from the system, that is B1 at t plus dt, and then we have to add region 2 at t plus dt. Now, based on this equation, B cis at t plus dt, which is appearing at the bottom of the slide, we have to move forward to reach to the Reynold transport theorem. Now, as the system is forwarding inflow of the control surface being through the edge A, F, C, and it is leaving out through A, D, C to the control surface. Now we shall embed this into our equation. The time rate of change of B in the system, we shall write d dt of B cis is equal to B cis at t plus dt minus B cis upon dt. This is the basic definition of differentiation of a function, as we write limit dt approaching to 0, the function f of t plus dt minus f of t upon dt. So that basic definition is coming from calculus. Now we shall substitute this quantity B cis t plus dt from the equation which we have raised out of the physical observation of the situation, and by substituting this we obtained the second equation appearing on the slide. Here B system and B control volume, they coincides at time t and they are equal. So here we are replacing this B cis by B CV. This is one important equation I am highlighting here because we shall be referring this equation in later discussion. Now this equation is subdivided into two parts. First two terms I am considering for discussion, then later on I shall discuss the last two terms. Now let us examine the first two terms, B1 upon dt and B2 upon dt, which we are talking at later point of time. However, at the earlier time there was no region 1 and region 2. Therefore, B1 of t and B2 of t is equal to 0. This identity also we are going to use. Now the influx B1 upon dt, which we can call as the rate of change of the region 1, rather b1 upon dt, we can call the rate of change of extensive parameter in the region 1 as time flows, and as we have seen in the earlier diagram, that is influx, and we can write b1 at t plus dt minus b1t, because b1t is 0, and that fits this equation to represent in the form of derivative b dot in AFC surface. This dot indicates the time rate of change of the extensive parameter b because of influx. Similarly, we can raise expression for outflux, which is pertaining to region 2, and the extensive parameter b in the region 2 per unit dt we can rewrite by exploring b2t, which is 0, and then it looks like, which is representing the outflux through the surface ADC we have referred in the earlier diagram. Thus, the influx and outflux in the first two terms we have represented in the form of time rate of change of influx and time rate of change of outflux through front face and the back face. So we are going to again deal with this pair of equation. Before handling that, we have to get into the surface representation and involved geometry related to that. Let us suppose that we have the outflow surface which is being represented by A, D, C, and influx surface of control volume as A, F, C. Now let us consider the infinitesimal small area dA on the outflow surface, wherein n bar represents a normal vector. Later on I am going to use this as n cap, that is a unit vector perpendicular to this surface area, and v bar is the velocity through which the outflux is leaving to the surface, and here this theta has to be less than 90 degree, then only it will leave to the surface, otherwise it will not leave to the surface. Similarly, at inflow, theta has to be greater than 90 degree so that it can get into the surface, the control surface, and here again dA represents the similar infinitesimal small area, theta is the angle involved, v is the velocity. So unless velocity is greater than 90 degree to n cap, n bar, the inflow will not occur. So with this idea, we shall consider this is the area dA and the flux is leaving to this area with velocity v bar in this direction, and let us suppose that n cap is a vector normal to this surface. Now in time dt with velocity v, the matter will advance distance v into dt, which we are representing as dl length. So this leaving component will describe a kind of cylindrical geometry, and dln is the component of dl in the direction of the normal unit vector. So dln is equal to dl into cos theta, and we are replacing dl by v dt, so we have v dt cos theta. We can conveniently write this using vector notations as v bar dot n cap dt. So this component is represented nicely using the dot product. Now we shall compute the outflux Here, as we have discussed, that intensive property B is extensive property per unit mass, and we can write dB equal to BdM. dm we can replace by rho dV. So dA multiplied by dl will represent volume of the cylinder, which we have expressed here as dV. Now dV equal to dA into dln is equal to dA dl cos theta equal to dA V dt cos theta. Now dB is equal to B rho dV, and now that we are replacing dV from the last equation, and we are left with B rho dA V dt cos theta. dB by dt is equal to B rho dA V cos theta, and now V cos theta we are writing as V bar dot n cap. This quantity is in fact the rate of change of the extensive parameter B in the outflow. Now this outflow we have considered for infinitesimal small area dA, and now we are interested in finding for the complete portion ADC that we have referred in the earlier diagram. So to do so, we need to integrate this equation. This will be the integrand, and it is to be operated over the area ADC. So this is a surface integration dA operated on area ADC. So B dot out we are replacing from this equation, and thus we have this quantity B dot out ADC. Similarly, we can raise B dot in AFC, and that will be with negative sign because we have unit vector in the direction leaving the surface. So in will have opposite direction, that is accounted with negative sign. Now the two terms, when we try to put together, we have B dot out ADC, B dot in AFC. When we subtract these quantities for first two terms, we have same integrand once operated over front surface, left side surface, and second time operated on right side surface, respectively ADC and AFC, that we can consider for complete closed control surface area. So the first two terms are reducing to this integration B rho dA V bar dot n cap integration dA. Now let us deal with the last two terms. The last two terms in our last equation which we were referring is BCV t plus dt minus BCV upon dt. This is in fact by definition rate of change of the extensive parameter B control volume, which is appearing on the right side. Now the total B in control volume we can obtain as BCV by operating integration over dB that rolls over the complete control volume. Now we know dB is equal to B dm, and dm we are replacing by rho dV. Now the time rate of change of B in CV, we have to differentiate BCV on both sides, and we obtain d dt of integration over control volume B rho. Now that we are almost done, here we have the equation which is appearing on the screen already established. Now we are collecting the terms together. B2 upon dt minus B1 upon dt at later time is equal to integration over closed. So thank you very much for your patience. Surface, which is control surface in fact, operated on B rho dA V bar dot n cap dA, and the last term in the previous equation, which is d dt of BCV is equal to d dt of integration over control volume B rho dV. So substituting everything together, we obtained the equation which is known in the literature as Reynold transport theorem, and it represents the time rate of change of B of the system on left hand side, which is equal to sum of two quantities. The first quantity is net outflux rate of B through CS, and the second term is accumulation rate of B in control volume.